Hello, this is the advanced manufacturing submission for my project on a simulation of laser beam machining. What I wanted to do with this project was to be able to take in some 2D projections of parts and upload them into a Matlab simulation so that we could output the time and the amount of energy required to cut out those parts. A bit of background on what laser beam machining is shown with this figure here. In this example, a laser beam is moved across some material in order to vaporize it to cut out a certain shape. There's a handful of inputs that are needed for Matlab that we can pull from this image in order to run the simulation. The first group of variables has to do with the laser itself. First, we look at the focal length of the laser, denoted with F. This is how high the laser is held above the material. There's also something called beam divergence, with alpha. What this is looking at how the beam actually expands as it leaves the laser body. Another quality of the laser is how much power is actually coming out of it, which is measured in watts. In the assembly of what you're running, you need to look at the ambient temperature of the room, denoted with T infinity. Looking at the material itself, there's a handful of qualities. So depending on whether you're cutting a steel, an aluminum, or some alloy, you would need to know the specific heat capacity, Cp, the melting temperature, Tm, and the latent heat of fusion, HF. Once we know the laser that we're looking at, the material we're cutting out, it comes down to the part. The first is how thick is the sheet of metal that you're trying to cut. We look at this using TH. Next, there's path length, which in this image would be cut along the x-axis. We measure path length by looking at these 2D projections here, where P would be the summation of all of these segments in this star image. The last variable we have to look at is the cross-section of the cut. We find this by looking at the beam diameter and the thickness of the plate. So if the beam diameter is along the y-axis, the thickness of the plate is along the z, and we can hash out that area as such to find AC and P for the path length. All of these inputs are shown here as variables, where the blue variables here have to do with the laser being used. The green variables have to do with the type of material being cut. And these orange variables have to do with the actual part that is trying to be machined. We can use these inputs to answer these equations below. These are the variables and equations that are input into the Matlab simulation, ultimately to pull out the time variable here. Knowing how much time is being spent machining is critically important for optimization of processes and saving of energy to cut down on manufacturing costs. Next, we'll move into what does the Matlab simulation look like and how do we run it. So this is the manufacturing Matlab code for laser beam machining. This code has been divided up into 4 parts, where the first part is the inputs. The second part is interpreting the cut path. The third part is the actual manufacturing equations. And the fourth part is the outputs. So looking into the first part, the only difference in this section, which includes all of these lines, is that we now have a file read of what we're trying to cut out. In this case, it's a bitmap image of a star that was shown earlier in the video. Also, we include a function to consider whether we want to cut the inside or the outside of that shape. Right now it's set to cut the inside. This is important if we wanted to cut out a hole on a larger part. We might want to cut on the inside of that part so that the hole could be used for a bolt. However, if we're trying to cut out that 2D projection and we needed that cut out piece, then maybe you want to cut on the outside of it. We also are now considering the resolution of the cut. This is integrated when we are converting that red file into a cut path. The higher the number is, the more pixels that are being skipped over. So for now we're going to leave that as a higher resolution so that the exact projection is cut out. The focal distance is the laser height, as we talked about, and we also have a ratio between how pixels are converted to millimeters. These are all previous variables that we discussed earlier. So now diving into the second part, which is tracing. This function series here has to do whether we are on the interior or exterior of the cut path. These k variables here are looking at whether you are on the inside or outside. 2 would be on the inside and a 3 is on the outside. We skip over 1 as that would be assuming the actual boundary of the entire picture that is uploaded. We run the boundary function over the path that we're looking at, and then we end up counting the number of segments that are used to create that boundary. We start off by saying the path length is 0, and by the end of this for loop here, we continue to add on to the path length. Path length is calculated by looking at individual points of the boundary and finding the shortest distance between those 2 points. Typically you could just go point to point to point, but because we can change the resolution, those points might not actually be tangent, and this function helps us get the shortest distance between those points. That concludes the second part. So the third part is looking at the actual machining that is done. These are the equations that we covered earlier in the video. First, we figure out the diameter of the laser, given its divergence and focal length. From the diameter, we can figure out the cross-sectional area of the cut. The evaporation energy are all qualities of the part and the room temperature. Taking these previous variables and inputs, we can find the feed rate of the machine. This is what is the linear movement of the laser along the path. We also convert the path length from pixels into millimeters. We calculate the volume of material being machined by looking at that cross-sectional area and multiplying it against the length. The material machined is the feed rate times the cross-sectional area. Using those past two calculations, we can now look at the time to machine by dividing the volume of material by the material removed over time. In the fourth part, we display those outputs, which might be useful for optimizing machining. This command here shows the file that has been uploaded. We then put labels onto the plot, such as the axis labels and the title. Last, we put on the cut path. This will show whether we are in the interior or exterior of the cut. So the file that has been uploaded is a star, shown here. And as we choose to run the file, we have a series of outputs shown in the command window, such as the feed rate, the cut length, and the machining time. Here is the total part to be machined, and as you see that thin red line on the interior, that aligns with the eye that we denoted on line 14. We can change that to be the outside of the part. Run it again, and the red line will now be plotted on the outside of the image. There is some difference between these. As you note, the machining time does go up slightly, and that is really a function of the cut length changing. This time might seem a little small, but given how small the actual part is, of only being 13 millimeters in length and a 74 millimeter per second cut speed, this does make sense.